Hi, welcome to Physical Science 3.3a. Today we're looking at potential and kinetic charts, graphs, equations, and then eventually in 3.3b we'll do calculations. So let's redefine what energy is. Energy is the capacity for doing work or producing heat. Remember that we have the law of conservation of energy. It says that energy cannot be created or destroyed. It can only be transformed from one form into another. Today, we're going to look at both types of mechanical energy, potential, e.g., and kinetic, e.k. Potential energy, e.g., we're going to look at a pendulum example. Energy, e.g., potential energy, is associated with an object's height above its normal position. So when the pendulum is raised from position D, its lowest point, to C, it has gained potential energy because I did work on it. When it is raised all the way up to position A, its highest point, or at least the highest point I could reach, all of its energy is said to be potential energy because it has the potential to fall. Now, kinetic energy, EK, remember, is the energy associated with an object's motion. It depends on the mass and the velocity of the object. When this pendulum moves from A to B to C, it will gain kinetic energy. When it reaches D, it's going to be moving its fastest, and it has all kinetic energy. So, energy charts. We're going to start with pie charts. They're a good way to visualize the amount of energy in its various forms. So, position A, remember we said, has all EG. Position D has all EK. So when we draw a pie chart for it, we're going to just draw a circle that says EG in it, and it's all EG. And at position D, we're going to draw a circle that has all EK. Now the colors really don't mean anything. The labeling inside is what makes the difference. Same example, as it swings to its lowest point, it's moving fastest, and all the energy from A, that was EG, is converted into EK because it's going the fastest at D. At points B and C, though, it's going to be a mix of EG and EK because it's gaining speed and losing height. So maybe B looks like this, where the EG portion is a little bit bigger, and C looks like this, where the EK portion is bigger. Again, a pie chart is just a nice way of looking at the thing as a whole. All of the energy is one of these two things. Charts to graphs. So even though pie charts are good, we're going to transition into using bar graphs. And in a bar graph, you get 4 blocks of energy, period, as if you divided those pie charts into fourths. Okay, so at A, we have all EG, so I would use 4 blocks of EG. At B, maybe we have 3 EG and 1 EK. At C, I know it's not half and half because it's not halfway between, so maybe 1 EG and 3 EK. And at D, it's all EK. Now, the chart, you can't have part of a block. And the chart is, again, not an exact thing. It's just a representation of all the energy in its various kinds. So, position A, B, C, and D. Pie charts to bar graphs. Finally, then, we go from pie charts to bar graphs to an equation. Now, the equation is not it's not something you solve, it's just something you write down. So you are given an example of a ball that's bounced. You're going to have to do the pie chart, the bar graph, and write the equation. So here's your example. At A, the ball has just bounced off the ground. Okay, and the green arrow means that it's moving really fast. At B, it's halfway to the top of its path, and it's going half the speed. At C, it's not moving. Notice there's no arrow next to it. It's not moving. It's at the top of its path. D is halfway down, and notice the velocity arrow is going down. And E is right before it hits the ground. So the pie charts, A would be all EK because it doesn't have any height off the ground, but it does have, it is moving, so it's all kinetic. B might be half and half. C is all EG. D is half and half. And E is all EK again, right before it hits the ground. The bar graph would look similar. All EK, half and half, all EG, half and half, all EK. Now the energy equation is literally writing down what kind of energy you have and where it's located. So essentially it's like reading the bar graph out loud to somebody. This would read EKA, meaning EKA, is equal to, because of the law of conservation of energy, energy cannot be created or destroyed. It just gets transformed from one to another. So that means it's going to get, you're going to have exactly 4 blocks every single time. So they have to be equal. EKB plus EGB has to equal EGC, has to equal EKD plus EGD has to equal EKE. It sounds like a mouthful, but again, it's just essentially writing down what the pie chart or the bar graph would be if you had to read it out loud. Okay, I am going to make some other smaller helpful videos on how to do these problems a little bit more. Thanks for watching. Okay, so I almost forgot to tell you this. This is your energy addition. You need to be sure that this goes into your notes. There are 2 other types of mechanical energy that we have to be able to use in our problems that you're going to see. The first one is called ETH. This is actually thermal mechanical energy, or thermal energy. This comes from friction, and it is only used when objects slow down to a stop. Like you ever rolled a ball across the carpet and it slows down, comes to a stop? That would be an ETH. The last one is an EEL. This is an elastic energy, and it's used when there's a spring in or with the object. You're going to need both of these to do the assignments. Thanks.